So, welcome to the second Advances in Data Science seminar of the autumn semester. We've got a bit of a finish feel to this one. So recently Manchester appointed Sami Kaski on a 50% basis to come, and he's joint between Manchester and Aalto University. And he's tasked with directing the Pankhurst Institute in Manchester, which is going to be bringing advanced technologies into healthcare, including machine learning. So really to set up a machine learning group in this new Pankhurst Institute and really bring some cutting edge machine learning into Manchester. Through that initiative, Manchester and Aalto hope to work together a bit more in the future. Aalto and Helsinki in general has really good expertise in AI and machine learning. They're one of the strongest in Europe in this area. And so we hope to benefit from some of that. And in that spirit, today's speaker is somebody who's moved to Aalto recently, but I'm not going to introduce Vikas. I think I'm going to leave that to Sami to do, since Sami knows Vikas well.
Yeah, thanks, Magnus, and thanks for the introductions. And hello, everybody. So I've never managed to join these meetings yet. So for some reason, I haven't got them to my calendar, but I'll improve my behavior. I'm certainly interested in joining these. And I'm very glad to introduce Vikas Garg here. So he started in Aalto University as an assistant professor, actually this semester, right after he worked in MIT with Tommi Jaakkola, Professor Tommi Jaakkola over there. So he has been doing highly exciting work besides the graph neural networks that he's going to talk about today. He has also worked on game theory, optimization, modeling of chemistry, proteins, amazing amount of work given his young age, and he's publishing in the main machine learning conferences several times a year. So Aalto certainly hopes that he will continue on this track. As Magnus said, as a part of the collaboration between Aalto and University of Manchester, Vikas is also interested, as I've understood, also to talking to people who might be interested in collaborating with him. So Vikas, the floor is yours. Thanks for joining.
Well, thank you so much, Magnus, Samuel, and Ola for coordinating this event and having me here. And hi, everyone. It's great to be here. And hopefully I will present something that would be of interest to everyone here. So why don't we get started? I'll just share my screen. Are you able to see the slides?
Perfect.
Great. So today I'll be talking about generalization and representational limits of graph neural networks. This is joint work with Stephanie Jagelka and Tommi Jaakkola at MIT. Okay, so we encounter relational and interactional data in our day-to-day lives. There are tons of examples, but just to motivate, here are a few. So we have these 3D interactions in actual geometric 3D objects like molecules. So here, for example, you have the atoms that are the nodes of the graph, and then you have the edges which represent the bonds or the forces between these atoms. So these are actual 3D structures. Then we all know about internet and other distributed computing paradigms. So here there are lots of machines which are geographically scattered in different locations, different parts of the world, and messages are being exchanged between the different servers and clients, as we all know. There are other kinds of dependencies. For example, you have the program snippets. Here you have these different variables and different modules, and one module calls the other module, and so we have this the interactions that come there. So these are the semantic dependencies, and graphs arise very naturally in such applications as well. There are more subtle kind of interactions. So, for example, you could think of countries in the United Nations who are negotiating amongst themselves in order to get votes from others. So some resolution comes, then these negotiations get started, and countries are trying to actively canvass votes from other countries. So you would know, like, for example, there are all these negotiations going on regarding Brexit, and so you could think of all this happening at a much grander scale with lots more resolutions, lots more countries involved, and we would like to understand who is influencing whom, for example. So this is another kind of data where interactions lies at the core in some ways, and these are very naturally modeled as graphs again. Okay, so being in machine learning, we care about certain things, and the most important thing that we care about is, for example, the prediction tasks. So what kind of prediction tasks, you may ask? So I'll just motivate with some tasks which are very common in the context of graph learning or the graph representation learning more broadly. So first example is here that of a graph property prediction task. So consider, for example, you are given this molecule, and we abstract it as a graph, 3D graph. And now what we would like to ask is to understand or predict the behavior of this molecule under certain mediums. It could be the solubility of this molecule in some medium. It could be the bioactivity of the molecule, and so on. So how do we define this prediction task? This is one type of problem that is of interest. Other kind of problems that's very relevant to online systems in general is the product recommendation application. So this is an example of a edge prediction tasks. So essentially you have two sets of nodes. One is the person's nodes, others is the product nodes. And previously you observed certain persons buying some of the products. And so you have these edges from the persons to the products indicating that they bought this. Now there are some acquaintances that these people have. These could be, these are the influences, like that could impact whether a particular person might buy one of these products. So you could think of this information coming from social networks like Facebook or Twitter or something of that sort. And now what we would like to predict is whether this particular person is going to buy one of these products or not. So you can do a targeted, you could have, like, for example, a targeted advertisement based on this understanding. Another kind of task that is very relevant in the context of graphs is a node prediction tasks. So for example, you have these 3D structures, and what we would like to do is to label the nodes in this 3D structure with one of the amino acids. So there are these 20 amino acids, and what we would like to do is to do protein design. So protein design is essentially an inverse problem to protein folding. So here we are given the scaffold or the 3D structure, and what we are interested in is predicting or is labeling each node. And this is a very important task, because if you try to carry it out in lab without AI, it can take like several years to do this. So we would like to get some good predictions in this, and that would directly help in problems like drug design. So there are other tasks that can also be phrased in terms of graphs, for example, graph to graph translation and all this. But for the purpose of this talk, I think we can just focus on these tasks. Okay, so now there are certain challenges that we must overcome before we can proceed to prediction. And the major challenge is, how do we represent graphs? So, we've all worked with natural language processing data or the image data. So you have these sentences or you have these images, but graphs present some different kinds of challenges that we don't encounter working with such kind of data. For example, first of all, there is no explicit ordering of nodes. In case of images, for any given pixel, you can order the surrounding pixels from in a clockwise manner, for example, or to say that like this pixel is at the north, this pixel is at the south, and so on. But in graphs, generally, we do not have that bit of information. Secondly, these graphs are very heterogeneous structure in terms of degrees. So in case of images, again, you know that there are four directions, or 8 if you consider the northeast, southeast, northwest, and southwest as well. But you know that the node degrees are pretty much same for all the pixels, but for some at the periphery of the image. In contrast, in case of graphs, we don't have this liberty, we don't have this flexibility, because the different nodes could have vastly different number of neighbors. So these are some of the main challenges in being able to represent graphs. So how do we embed graphs into vectors so that we could subsequently use them for prediction? And that's the focus of the talk. Okay, so graph neural networks are state-of-the-art models which are essentially geared towards this goal that we would like to produce node, edge, and graph embeddings for a specified end task that we have. So the idea would be that we are given, as I said, that we are given an input graph, and we would like to find a vectorial representation or a real representation of the graph. And the way a graph neural network works, it's an iterative procedure. So if you have T layers in a graph neural network, then you will have T updates for each node. And the way it works is that a node, it collects some information of the current embedding of its neighbors, and based on this, it updates its embedding in each iteration. And each of the nodes does this task, and like after unrolling for T layers, at the end of it, we will have embeddings, the refined node embeddings for each node. And now you could use these embeddings, for example, for predicting the label for the node. Likewise, you could have edge embeddings, and you could predict the product recommendation task that I was mentioning. Or you could combine the individual node embeddings that the graph neural network gives you. You can combine them into an overall embedding for the graph and ask about problems like molecular property prediction, so which is a property of all the nodes and not specifically of an individual node. So this is the overall idea. And these graph neural networks are essentially the state-of-the-art models. So previously there were these kernel embedding methods, and lots of work, in fact, like a couple of decades of work preceded this line of work on graph neural networks, but these models are essentially the state-of-the-art art today. And depending on how exactly you refine each node refines its embeddings. There are certain kinds of aggregation and update rules, and different instantiations give you different kinds of formulations, the exact criteria that you optimize for. And these are some of the earlier papers where the update was. So there is, for example, one paper on graph convolution networks, which is a counterpart to the GNNs for images, for example. So depending on how you precisely define the update rules, you get different methods, but the overall generic framework is what I just mentioned. Okay, so let me get to the agenda for today. So this talk will essentially be focusing on two parts. One would be regarding the representational limits of graph neural networks. So here I would illustrate some constructions to show that even though we have very powerful graph neural network variants, they still cannot distinguish between non-isomorphic graphs. So we will be seeing cases where there are graphs that differ in important graph properties, but no matter what's the depth or the width of the graph neural network that you take, so long as we stick to the paradigm I mentioned about nodes exchanging only local messages in order to update their embeddings, we can show that there exist pairs of simple examples of pairs of graphs that no GNN can essentially distinguish. And so this is more like a worst case analysis where we are trying to understand what are the inherent limitations of GNNs, specifically what they cannot learn. So they cannot learn these graph properties essentially That this is one part of the talk. The second part, we will try to understand the generalization ability for graph neural networks. And as machine learning practitioners, what we do care about is how well we are able to do on the test data or on the unseen data, which is sampled from the same distribution as the training data. And so it's not just about the representation is only one part of the story, because we say whether these models are rich enough to capture the semantic information from, or semantic signals from the graph data. On the other hand, generalization tries to understand whether we can meaningfully predict. So whether our test error would be low given that our training error is small. So how well we will do if we see new data that was previously not made available to us as part of the training. So this part in some ways is about understanding how well can GNNs learn when they in fact can learn. So this is the second part of the talk. So let me clarify some things, that when I talk about good representation, there are two parts essentially that we should care about. One is ability to distinguish dissimilar graphs. So we would like, if two graphs are highly dissimilar, we would want their vectorial representations to be, or the d-dimensional vectors to be far apart. The other part is we would like to assign similar embeddings to graphs that are almost or nearly similar. But for the purpose of this talk, we will only concentrate on the first of these, which is to understand their ability, or rather the inability, to assign distinct embeddings to some dissimilar or non-isomorphic graphs. This is an important distinction to keep in mind. Okay, let's dive right into the representation limits. Are there any questions at this point before we move to the to understanding the representational limits? I guess none, so I'll just continue. Maybe please feel free to ask questions like at any point of time. I don't know if you're writing in the chat window. I cannot see it at that point, so I guess Magnus or Orla, you can ask these questions later. Okay. So before we try to understand the representational limits, let's dive a bit deeper into the working of a graph neural network. So I introduced a general paradigm. Let's take a concrete, let's take a toy example to make this discussion a bit more concrete. Let's say that you are given an input graph of 5 nodes, and we will focus on node A for the time being. What we have in input is initial feature vectors. So these could be, for example, if you consider a molecular graph, for each node you will have the atomic number and so on. There could be also features on the edges which would pertain to the bonds. But we will, for now, let's just focus on the embedding of a node. So we are interested in understanding how the embedding evolves as we pass this graph through a graph neural network. So what's the action of a graph neural network on this toy example? Let's focus on node A. So so consider a two-layer graph neural network. So the embedding at time 2, so this is the final node embedding that we will have for node A. It depends on its own embedding from previous time step, as well as the embedding of its neighbors, which happen to be B, C, and D in this case, their embeddings from time step 1, the previous time step 1. In turn, each of these neighbors, for example, B's embedding would depend on their neighbors, which happen to be A and C in this case, and so on until time t equal to 0. And at time t equal to 0, as I mentioned, the embeddings are the initial feature vectors that come with the graph. So this is how it works. In the gray blocks, you essentially have the weights or the parameters of the graph neural network. These weights could be shared across different layers, in which case you get a recurrent formulation of the graph neural networks, which is reminiscent of the recurrent neural networks. On the other hand, if these weights are distinct across layers, what you get what is called typically a stacked GNN formulation. So these are just two different paradigms. All the results that we will be talking about today, they will apply more or less to both of these settings, shared weights or disparate weights. So the way, as I said, you could essentially think of two operations happening here. First, a node at any time step aggregates the current embeddings of its neighbors, and then it combines it with its own previous embedding and or its initial node embedding to get a refined embedding for itself. And this procedure will be repeated for t layers where t is the number of for t steps where t is the number of layers in the graph neural network. Okay, importantly, like one of the things that we would be using, we will be invoking repeatedly in our talk would be this notion of computation tree. So as the way I explained this, we could trace the evolution of the embedding of any node in terms of this computation tree. So the node would be, the node of interest forms the root of the tree, and then the flow of information is from the leaves bottom up. And so here, as I said, that A receives information from B, C, D, they receive information from their neighbors and so on. This is nice because a graph, as you know, it could have cyclic dependencies. And so it's typically hard to understand or play with the information flow when it's going around in cycles or circles. But by using this notion of computation tree, we've been able to, we can just analyze flow in one direction, which is from leaves to bottom up. So this was a computation tree for node A, but likewise, you will have computation trees for other nodes as well. And once you have this procedure, each node at the root will give you, at the root of the tree will give you an embedding, final embedding for the node in question. And once we have these embeddings at the root, we can combine them together via a readout function. And this readout function could, for example, be a sum or just like a mean or element-wise max. So this could be any of these. For the purpose of this talk, we will focus on permutation invariant readout functions, which means the ordering of the nodes does not matter when it comes to the final embedding for the graph. I hope the setup is clear. Okay. So regarding the representation, why do we care about the questions regarding the inability of GNNs to find certain patterns in graphs? This is a motivating example. So consider this these several drugs, paracetamol, penicillin, and all this. So they exhibit certain patterns which are crucial to predicting their properties, or which define their properties in some ways. For example, these cycles, these benzene-like cycles, they are super important from a biological perspective. Then properties like conjoint cycle, where two cycles share an edge, that is also important. The number of cycles, the diameter, the types of the functional groups that you have, all these are crucial ingredients or substructures that go on, that in a large way define the overall property or the behavior of the molecule. We abstract these in terms of mathematical objects, which in this case are graph properties. And some of the properties that we focus on are the standard properties. For example, the length of the largest cycle or the shortest cycle, the diameter, the number of cycles, then whether there are some cliques or strong or fully connected components within the graph, and so on. So as I mentioned, that graph neural networks have registered astounding empirical successes recently across domains. So you would think, oh, these tasks should be, learning these properties should be a simple task, but unfortunately, it turns out, as we show in one of the recent works, is that GNNs that use a permutation invariant readout function, they fail to distinguish simple pairs of graphs that differ in some of these properties. So yeah, so just to give you an intuition, or just to why that might be the case, here is a counterexample. So you to consider two graphs. The first graph consists of two triangles, and these are identical components. So the nodes marked B, they have similar identical feature vectors, and likewise for C and D. And the second graph here is a single cycle of 6 nodes. Clearly, these graphs differ in several of these properties, but it turns out that we cannot distinguish any GNN which relies solely on local messages, as we discussed, cannot distinguish between these two graphs. And so here is a proof idea or intuition. You consider, for example, consider node B from the first component of first graph, and let's say that you fix the depth of the graph neural network to level to 2 layers. So clearly we see the computation tree. This is all we need to precisely characterize the embedding that we will have for node B at the end of processing by the graph neural network. Likewise, now take the pointed or the indicated node from second graph. This is another node B, and we again get an identical computation tree. It does not matter how you could we could use an induction argument over the number of layers. You could have arbitrary number of layers, but these computation trees would be identical. So this is not just like restricted to only node B, but even the other nodes that you see, C, D, from the first graph, they would have identical computation. They would have a corresponding node in the second graph with identical computation trees, because the initial features that you start with are identical. The updates that each node makes are identical. So at the end of it, you will get the same multi-set of embeddings for the nodes in the two graphs. And hence, if you use a function, a permutation invariant function like mean, etc., you won't be able to differentiate them. They will map to identical vectorial representation for the graph overall.
Vikas, I just want to, Stefan's put a question in the chat, and
Sure.
I think it might be good to ask here because it's to do with this part of the talk. Stefan, do you want to ask it or do you want me to?
Oh, I can quickly ask it. So I was just wondering, so when you discuss the ability or inability of a GNN to distinguish some graph features, right, I assume that you would take the number of nodes, like the number of input features, to be the same, right? Yeah, I'm just asking because these molecules on page 14 that you showed, they would probably be represented by graphs of different sizes.
So as you see, like the total number of nodes here is 6. If you like this, and for first node there is a corresponding node. So you would have to. So for example, there could be some graphs which cannot be differentiated by mean, but they would be differentiated by sum. So if I had taken, like, for example, only the first component for the first graph and the second graph, you could just tell by counting like the number of, you could just like, if you take the sum embedding, then one would possibly give you a different one. But
right.
But then you can increase like the number of components. For example, you could construct like one for a 9-node graph, and you could possibly do that. But that's a great question. Exactly. There would be, depending on the readout function that you use, you might have to, you need to ensure that the number of nodes is same. And also you need to essentially construct these cycles in a slightly subtle way, so that you get the same trees, computation trees reproduced for both graphs at every level. Otherwise, you can find a counterexample that, okay, you cannot. So one like simple thing to do, for example, could be that you could have a tree. You could just express computation trees for a particular depth. So for any graph, you could construct computation trees for the nodes that would have identical behavior up to a particular depth.
You truncate.
So you could, so you could do that. It's a great question.
Okay, thanks.
Yep. Okay, so the other thing is, you might be wondering, okay, so this seems like a standard paradigm. So have people tried to devise more powerful variants? They have, and part of these models have been inspired. Some of these models have been inspired from prior work in distributed computing and graphical models. So one of these recent models is called the consistent port numbering graph neural networks. Here, the idea is that if you try to understand, one of the problems with the standard graph neural network paradigm was that we were treating all neighbors equally for each node. So we were simply aggregating the messages that were coming. We were not really differentiating the neighbors. So the idea of consistent port neighboring GNNs is to consider to assign ports, local ports to the neighbors of each node, so that you can receive more pointed or directed information to and from your neighbors. So that is probably a more powerful paradigm, because now you at least know about something more about the local structure rather than just knowing the aggregate statistics of the neighborhood. And so one of the ways like that, for example, this works, we saw a previous example where graph neural network could not tell two distinct graphs. Let's revisit that example. So here you again have the same two graphs, but now we've done a consistent ordering, local ordering of the ports. And now the node D2 in the second graph, this gets receives message from node C2 in second graph at port 2, whereas in the first graph it gets the message from port 1. So this way you can distinguish between the representation for D2 that you will get from the two graphs would be different. And the way it works is because you built now a more sophisticated aggregate function that takes into account the ports from which the messages arrive as well. For the rest, so even with one layer graph neural network that takes port ordering into account, you will be able to tell these graphs apart. The other paradigm that has specifically been proposed in the context of molecular graphs is this notion of directional message passing, or DIMNet for short. And here the idea is that instead of directly embedding the nodes, which are essentially the atoms in this case, you first embed the edges, taking into account the other local edges in the neighborhood. So you will take into account the angles for this edge with respect to the other edges, the length of this edge, and all these considerations. And again, this is probably more powerful than ignoring the local structure altogether. So you would think that like we already built more sophisticated graph neural networks like the CPN, GNNs, and DIMNet. It turns out, unfortunately, that there exist some consistent port numberings with which CPN, GNNs cannot distinguish these different graphs. And similarly, you can come up with counterexamples for DIMNet. So one of the issues with, I should point at this point is that CPN, GNNs, it's not clear what's the right ordering a priori, because no one gives you, when you are given a molecule graph, no one tells you what are the right port numbers to work with. But all we are saying is that if you do not do these things smartly, there are possibilities that you might not be able to distinguish the distinct or non-isomorphic graphs. So you could, regarding the proof idea, I'll just give you a very brief idea. So you could have port-ordered computation trees to articulate about why why CPN, GNNs would fail on the shown example here. But there can be more mathematical arguments that avoid having to construct explicit bijections. This is a proof technique that I will not go into detail here. Likewise, for the directional message passing now, because we need to take into account the local geometry, the 3D geometry like angles, distances, and all that. The idea is to embed graphs on cube or more three-dimensional objects, and going beyond the two-dimensional cases that we focused on. Okay, so I'll mention a couple of open problems or active areas of research in this field. First of all, the numbering matters in CPN, GNN, as I said. So the first example is where with the numbering you can distinguish. This is what I'm replicating the example from before. The other one is that you can come up with a different ordering on the same graph, and now they cannot be distinguished anymore, even with consistent port numbering. So the issue is, how do you come up with a good numbering? Because if you do a random numbering, then you might miss on the similarities that exist between nodes in some ways. If you assign arbitrary orderings, on the other hand, how do you decide? You could either be, you could either say that like two graphs which are dissimilar, you would not be able to tell them apart, or you would lose any notion of similarity that might exist if you use a random ordering. So this is one thing which is not clear. How would you come up with a good numbering scheme? The second active area of research, and this is a central problem, is how do we design more powerful GNNs? And this is also motivation for part of this work. Can we theoretically inform better models that are not constrained with some of these restrictions? So here is an example that if you incorporate the 3D geometry, if you go beyond the immediate neighborhood, and if you take, for example, the angles that are subtended locally between the different nodes, then you can essentially avoid some of these constructions. Then you can, of course, create other counterexamples for this, but this is a strictly more powerful class of graph neural networks than the standard GNN paradigm. So this is an ongoing area where like lots of energy has been invested into, and people are really trying to push the frontiers, trying to come up with more powerful GNNs than the prior art. There are other things that people have been focusing on. For example, there are higher order GNNs. So rather than just considering neighbors, you go beyond them and you consider, say, k tuples, so of all vertices. There are also message passing algorithms that take the underlying topology into account. Recently, there have been works for taking dynamic graphs. So rather than assuming that your graph is static, you also take into account the dynamics. And in other work, we also focused on the strategic aspect where your nodes are not passive entities, but they could be strategic agents. For example, I mentioned there could be several players. How do they reach decisions on a network when they are interacting with some of the other neighbors? So all these can be thought of as the current trends in this field. Okay, I will quickly jump onto the second part. This is going to be super brief because a lot of it is mathematical intuition. I'll try to convey some of it. So what's the deal here? We have a standard prediction pipeline, which in the context of machine learning pipeline, and in the context of graphs, this can be stated as follows. Our training data consists of pairs of graphs and their corresponding labels. These labels could denote, for example, some property of the graph. And now we use a model. This could be, for example, coming from a family of graph neural networks. So we try to learn model parameters as part of the training. Once we successfully completed the training, then our task is to be able to predict well on new graphs. So we sample our test graph from the same distribution as the training data, and we would like to predict the property or the label for this graph. And the generalization question is, how well can we do this task? Okay, the setup for generalization of graph neural networks is like this. We have a mean field update. Essentially, we are assuming that the aggregate function that you use when each node aggregates the information from its local neighborhood, that this is permutation invariant, which means the ordering is not taken into account. So this analysis would not hold for the CPN GNN, the consistent port numbering graph neural networks that I mentioned. So any such permutation invariant function under mild regularity conditions can be expressed in a sum decomposable form as shown here. So we can directly invoke that result previously published in certain works. And the way we set up generalization is as follows. Each node, the GNN acts on the graph. At the end of say T layers, you will get an embedding for each node. Now, each node employs a binary classifier, which is bounded in norm, and makes a binary prediction. And now we take the majority prediction as the overall prediction of the graph. So this is the setup that we are considering. We assume that the graph label is generated in this way by taking the majority prediction of the individual nodes. So a standard result from learning theory, which can be stated as follows in the context of graph neural networks. We essentially have a high probability result that the prediction error of graph neural networks can be bounded by sum of two terms. One is the expected training error. This is how well in expectation you perform over the training data, whether your training error is low or not. And second, the inherent capacity of the graph neural network to predict label from the graph. So if you are given a graph, how well can the GNN predict the label? And there are different notions to quantify this. For example, Rademacher complexity is one notion. You might have the Pack Bayesian, you might be aware of the Pack Bayesian analysis. There are VC dimension based analysis, but this is this is like the overall result, that with high, we will be sticking with the Rademacher complexity for our purpose. So this is the standard result stated in terms of graph neural networks. In our case, for the setting that we suggested, the majority prediction, we can show that with high probability, this bound can be simplified as being a sum of two terms. One, the expected training error as before. Second, we can now focus only on the capacity of GNN to predict label from an individual computation trees, which is nice because now we've eliminated the loops, as I mentioned, since the flow of information is only unidirectional from leaves bottom up to the root. So this is nice. We can simply analyze trees instead of graphs. Okay, so what are the insights? How does this help us? So let me sketch two essential intuitions into this. Consider this graph, and what we are interested in, for example, is sketching the embedding at the root, which is B1 in this case. So similar computation trees would exist for the other nodes as well. Let's consider a two-layer graph neural network. The embedding of node B, the final embedding of node B would depend on the embeddings of its neighbors from layer 1 after being processed with layer 1 and so on. And so the nice feature about this is because we have this computation tree, and we can recursively express the embedding for a tree node in terms of the nodes at its subtrees, all the way till the leaf. So this is nice because we precisely can bound can bound in some ways the effect of each of the subtrees all the way up to the root. The second thing that we do here is we do a perturbation analysis. So the idea is that suppose you've trained a GNN with certain weights. Now, if you change the weight slightly, then the embedding of the root would not change by much, so long as the spectral norm of your weights is bounded. So if your GNN parameters are coming from a family of bounded norm weights, then small perturbations don't change the embedding of the root by much. And now, because each node is using a norm bounded classifier to make a prediction, that means the predictions themselves cannot change by much, and hence you get stability in predictions, and this stability in predictions directly translates into good generalization performance. And this is the key intuition for this analysis. Okay, to summarize, essentially what we get here is based on our analysis, we are able to provide the first data dependent bounds for graph neural networks. The bounds depend on a term, percolation complexity, which is inspired by branching processes. And the idea is that for different values or different regimes for this complexity parameter, we get different kinds of bounds. Specifically, our bounds scale linearly in the embedding dimension. So this is the dimension or the width of the graph neural network. You see an inverse square root m dependence on the number of the size of the training set. This is not surprising because even VC dimension would give you something similar. We also have a linear dependence on the number of layers, mostly, and that's that we have, and linear dependence on the max degree of any node. To say like why these are meaningful numbers, we can essentially see the corresponding numbers for the VC dimension bounds for graph neural networks, as well as the recurrent neural networks. So For recurrent neural networks, we essentially recover the bounds, the tightest known bounds for recurrent neural nets currently, by setting D to be a constant, because recurrent neural networks typically are used for embedding sentences where the degree is more or less can be treated as constant. But our bounds are significantly better than the VC dimension bounds, which are data or distribution agnostic bounds, where the dependence scales cubic in the embedding dimension and linearly on the size of the graph. Now, the degree of a max degree of a graph could be substantially smaller than the total number of nodes in the graph, so we improve on both fronts. So these generalization bounds can be extended to the consistent port numbering also. We outline the essential parts of that approach in the paper. I encourage you to look up and follow up with me if you are interested in following that analysis. Essentially, we can use a port numbering notion to quantify the complexity, and we can get a generalized some decomposition form that disentangles the messages from the ports that they come from. So this buys you richness, but the bounds would be worse because you have a richer class that you are working with. Okay, so we talked a lot about lots of messages, but for this talk, I will just want you to have one take-home message that both representation and generalization are equally important. The model should be expressive enough to fit the data that we have. At the same time, we ultimately care about the downstream task, how well we are able to predict. There are often trade-offs between expressivity and generalization. Richer models tend to overfit. So depending on your application, you might want to spend some time thinking what's the right trade-off. There are also trade-offs similarly between expressivity and computation, because you can build more expressivity, but then you would perhaps also need to spend more on computation. So the ideal trade-off would often be dictated by the application at hand, the amount of data that you have available at your disposal, and some additional constraints that you might have, for example, on training and inference times. For more details, please take a look at this paper. This is a recent ICML work. And anyway, if you have any other questions, please feel free to ask now or follow up with me later. Thank you.
Thank you, Vikas. Let me ask if there are any questions from anyone. You can either speak up or you can type into the chat and I can ask Vikas. So while people are thinking, so I mean, these bands are a lot tighter, you showed, than the VC ones. But how tight are they? So, I mean, I always have, I mean, are these practical things that we can use really when designing graph neural networks on real data? Are they sort of practical in that sense, or do you think it's more about getting insights into these?
So lots of things are, that's a great question, Magnus. So one of the things that I would say is insights is what we are essentially looking for here. So if these bounds might still be vacuous if you like actually experiment on small data or something, because that's I think that's true for the recurrent neural network bounds as well. And so because we say that we are comparable to those bounds on certain kinds of data, it might be tight on some certain kind of data, but there could be data sets where these bounds are still loose, but they are considerably stronger than the VC bounds. And the insights are that, first of all, the distribution does matter. VC is distribution agnostic. So the first thing is the data that you have at your hand, that is crucial. So that should certainly form an important point. And that is reflected here in the gamma or the margin term that you see in the denominator. That's where the data dependence comes into picture. The bounds are significantly tighter than the VC dimension bounds. For example, as I mentioned, we are doing subquadratic in terms of the embedding dimension. In most of the regimes, it's only linear in R. R is the embedding dimension here. Whereas in case of VC, you have a cubic dependence on the embedding dimension. So if you have 100 dimensional vector into which you are embedding, then you can see like it's already VC is pretty much hopeless in this scenario. Also, with respect to the, as I mentioned, that R dependence is linear in terms of the max degree of any node, which can be substantially better than if you have, for example, like typically sparse graphs or molecular graphs. They have very few connections rather than
yeah, I was going to ask about that. So this max degree linear scaling, is that because you choose this permutation invariant function form,
yes.
or do people use that always in practice, or do people use more generalized types of functions where this wouldn't hold?
Yeah, so the people standard, like the standard GNN is mostly about me using this, like permutation invariant aggregate functions. So typically people use that. CPN GNN is a more recent advancement where they do take into account the port numbering into, they do take into consideration the port numbering as well. But as I said, that we outline an approach where you can, we outline an approach for obtaining the generalization bounds for CPN GNNs as well. We don't fully solve the problem because we don't do the full analysis, but we sketch an approach, and the idea there would be to disentangle the messages from the ports that they arrive from, and so this builds more richness into the model, but the bounds also become substantially worse. So yeah, so in short, yes, people typically use a permutation invariant aggregation function. That's the go-to. By default, if you see the libraries, you will actually see permutation invariant functions like mean or sum being used there.
So then there's a question for Stefan about, is there a good intuition about what overfitting means in the context of GNNs? So does it have a different feel from, function approximation or in other kinds of model?
Right. So the idea would be, again, that you could, there would be examples, for example, where you could do really well on the training data, but then you would not really generalize well. In fact, like if you see some of the molecular applications, this is one of the main concerns of the community, that when you try to predict properties for the molecules or try to do some things about molecules, they don't really generalize to test data. So most of these methods of the data sets, they work well so long as your training data, so long as your test data closely mimics or mirrors the training data, which is, but they really suffer in terms of their performance once you show them some examples, some test graphs that differ substantially from your training data. So this is in fact like one of the domains where we have enough empirical evidence to suggest that overfitting does take place, and that's
one thing I always find paradoxical about highly over-parameterized deep neural networks is that memorizing the data doesn't always correspond to overfitting, as long as your model is kind of smooth in substance. You can memorize and sort of deal with that. Are GNNs a little bit more like the older intuition of parametric models somehow, or there's perhaps a little bit more constrained? So maybe does overfitting correspond more to, if you memorize things, you overfit more, or is that not the right way to think about it?
So I would say that's a great point. Like if you ask me, my feeling is that from what I like the kind of intuition that I built around this, I feel that these are somewhere between the parametric and the non-parametric class of models. So you could think of, so it's like for the purpose of graph embedding, let's say that you are trying to represent the overall graph by a single vector. So you could think of as these different nodes as being catering to different parts of the space. So you could think of fitting a parameterized classifier, like a parameterized learner for each of the different regions of space, and then you combine them to get like an overall thing. So you can think of it as like some kind of ensembling effect taking place where the where each of the node so you do have some sharing of the parameters, which essentially means that you don't have a fully non-parametric settings here. So I would say that it's somewhere between the parametric and the non-parametric form, and the idea is being able to generalize from the patterns that might be present in one region to the another. So you get like some kind of understanding in each of the regions, and then you're trying to say that, okay, could we reuse some of this understanding elsewhere? So I think like that would be yeah. So and in some ways this is like a decision tree kind of thing also, like the random forest kind of thing also, like where you have these ensembling effects taking place. And the way I presented this talk in terms of computation tree, so you could think of as you could represent each graph essentially as a multi-set of computation trees. And now we are saying each of these trees is making you a prediction, and your overall prediction is a combination of these. So if you take, for example, a linear combination of these, so you have that power inbuilt, which comes out very naturally in terms of in the context of graph neural networks.
Right. There's another question in the chat, actually. I don't know if Nika wants to ask this. If you're there, you can unmute.
Sure, yeah. What is the, I'm just going to read it. What is the ETA for the higher dimensional directional GNNs that you mentioned with the angles to the planes?
What, sorry?
What is the sort of estimated time of arrival for the higher dimensional GNNs where you have explicit angles to planes, for instance? You could, I imagine, extend that relatively easily to higher dimensions as well.
So this is like whatever I discussed, this is typically done in a synchronous setting. So all the messages that you can pretty much assume them to be arriving at the same time.
But you said that you said that they weren't, it's an active field of research with these angles to the planes being introduced.
So this is, so yeah, so the all like I was trying to convey is that, so there are two paradigms, the standard GNN paradigm that does not really differentiate between the neighbors. So all you say is that each of the neighbor contributes some message and you weigh them equally. That's what essentially it does. So you take, like, for example, a simple average of that. On the other hand, in case of the port numbering models that you have, you take the local structure into account. For example, for each edge, you will see what are the angles that it subtends with the other nodes. So this is only, first of all, this is, let me remind you that this is only in the context of geometric graphs, actual 3D objects, because you cannot, this does not apply more broadly to general graphs, which is an abstract term, where angles may be pretty meaningless. You don't have like any angles between interactions between countries, for example, or on the internet.
I think Nika's question is more about, is the limitation to going in this direction just computational, or are people just not found good implementations of this yet? Is this something that's, you know, close to being applied, or is it here yet?
I think that's a great question. I think the issue is the implementation can be straightforward. Implementation is not an issue. I think the issue here is, how do you define a good port numbering? How do you, for example, so the directional message passing algorithm is already there, like specifically the DimeNet algorithm, and it seems to perform better than the message passing. There is this paper by ClickPera and which is iClear 2020, where they say directional message message passing has been introduced. So it gives really good performance improvements on certain molecular data sets. So that is easy to implement. The question is more regarding this directional message passing does not extend to general graphs, because you, by definition, you are only working on geometric graphs. So that's their inherent limitation, that they cannot be extended to to applications beyond such data. The issue with port numbering kind of things is that it's hard to come up with a good port numbering, because what does it mean? You want to preserve, in some ways you want to retain the similarities between similar substructures across graphs. So if you arbitrarily define port numberings, then you might lose those similarities. On the other hand, if you don't choose your port numbering well, then you will suffer from some of the other effects that I mentioned. So the notion, and I think like part of the issue is that these models have been ported from the distributed, or have been inspired by the distributed computing literature, where you care about a given problem at hand. You don't really care about generalization and being able to do well on future data. So those are some of the inherent problems with this. Implementation wise, there are no issues. You can pretty much implement them fairly easily.
Perfect.
Okay, thanks. I think we have to wrap up now because we come to the end of the session. It's really fascinating. I think a lot of people are trying out graph neural networks. It's a big kind of area where people are getting into applications, and I think maybe people will want to follow up with Vikas and sort of get his ideas on things, because he's clearly been thinking about this deeply. So it was a great talk. I think there'll be some follow-up discussion, and let's all thank Vikas. We can't do it in the traditional way. He just has to imagine us all clapping. I'm sure we are all. And thanks for everyone for joining us. There'll be another of these seminars in 2 weeks. Yes, people are doing virtual clapping. Let's do some virtual clapping. Here we go.
Yeah, thanks for having me. It was great speaking with everyone, and I'll be glad to follow up. Please just shoot me an email, and I'll be happy to respond as soon as possible.
Yeah. Okay. See you next time, everyone.